Hello, you're listening to The Conversation Weekly, the world explained by experts, and I'm Gemma Ware in London.
I'm Dan Marino in San Francisco, and today we are rerunning a story we did back in 2021 about dinosaurs, and specifically what they really look like.
I'm excited about this new Jurassic World Dominion film that's just come out in cinemas. I haven't seen it yet, but I've seen some posters and some trailers for it, and I'm always interested with these films and what they get right and what they get wrong about what dinosaurs actually did look like.
What paleontologists know about what dinosaurs actually looked like has changed so much over the last couple of decades, and we're definitely still a long way off from really pinning a lot of the details down.
So we had a lot of fun putting this story together, talking to a couple of paleontologists about this, and we hope you enjoy it too. So let's just jump straight in.
For Maria McNamara, as a kid growing up in the 1980s, her dinosaur knowledge didn't come from TV nor Hollywood, but rather from her grandma.
She was a big reader, was always buying books. She had a library at home, but she also was a hoarder. So she kept everything. So I had books that were up to date, but I also had access to books going right back to the 60s and even the 50s when her kids were growing up.
Today, Maria is a professor of paleontology at University College Cork in Ireland, and there are probably very few people on Earth who know more about what dinosaurs looked like. And that's why I wanted to know about the first dinosaurs she ever saw, the ones lurking in her grandma's old books.
They were green, usually, scaly, big. They didn't quite look like the ferocious predators that we know many of them were, and we certainly didn't see any small dinosaurs. So I suppose my concept of dinosaurs was pretty exclusively of large, green, scaly creatures, with very little of the nuance that we have today.
That nuance started to emerge in the 1960s during a period of time known as the dinosaur renaissance. New fossil discoveries and new research turned the scientific notion of dinosaurs on its head, from large, slow-moving, cold-blooded reptiles into warm-blooded creatures of all sizes living in a diverse ecosystem with reptiles and eventually birds and mammals too. But the surge in research had created as many new questions as it answered, and even stirred up some old debates. One debate was particularly hot around that time, and it had to do with the relationship between dinosaurs and birds.
Were they sister groups? Did they share a common ancestor? What exactly was the nature of the relationship between those two groups?
A lot of these questions hinged on feathers. Feathers had been pretty rare in the fossil record up until then, and for the most part, any fossil that had some feather was considered an ancient early bird. But then, soon after Jurassic Park first aired in 1993, a series of new findings from Zhejiang province in China changed everything.
In the mid-1990s, there were some literally quite spectacular discoveries of feathered dinosaurs, from China. It's called the Zhejiang biota.
These fossils all came from a volcanic region of China with a lot of lakes. And there are thousands of these fossils. Birds, dinosaurs, early mammals, all excellently preserved.
The first paper that was published was on this dinosaur called Sinosauropteryx. And it preserves some kind of brown furry stuff associated with the head and the back and the tail. And when you look closely at it, it just looks like hairs, short little hairs about a centimetre long. And they were interpreted quite controversially back then as primitive feathers. There was fairly intense debate for at least 10 years about what those features were. What that paper did was really quite remarkable, because by demonstrating evidence for feathers in a dinosaur, they were effectively providing direct link of the avian dinosaur relationship. And also they were showing that feathers aren't unique to birds, they actually evolved much earlier.
The discovery of feathered dinosaurs certainly changes what I imagine in my mind's eye. But feathers offer so much more to paleontologists than just the costume change.
Sinosauropteryx is a good example, actually. It was a small theropod dinosaur. So it's part of this lineage of dinosaurs that is most closely related to birds. And it was only about at most a meter long. It was, completely terrestrial. It was a runner. And we know that its feathers could not have functioned in flight because they were too short. So what was it using these feathers for? Well, if you look at the distribution of these structures over the body, they're everywhere. They're on the head, they're on the back, they're on the tail. And so because of this, it actually is much more consistent with functions in thermoregulation, in maintaining your body temperature. And it was a new line of evidence for when dinosaurs started evolving more bird-like metabolisms. And so we're starting to build up a picture of dinosaurs acquiring bird-like characteristics piece by piece. We call this mosaic evolution because they don't just evolve all of the pieces at once, they come bit by bit.
And some of the pieces of that mosaic were really wild. Take the Microraptor, discovered in 1998, for example.
It caused a real stir because it had feathers not only on the forelimbs, but also on the legs. So it's effectively a four-winged dinosaur. And still, there's ongoing debate about how this creature flew. It has long feathers. And what's really interesting is that its feathers have the full complexity that we see in modern birds. About half of the specimens that have been recovered have a weird tuft of feathers at the end of the tail. It's thought that maybe this is a feature used for signaling. Potentially by males, we don't know. It's really hard to actually sex these specimens because the bones are frequently fractured and compacted during compression as they're buried. But there are dinosaurs where we're pretty sure that feathers were being used for communication.
One of the dinosaurs that used feathers probably for communication was that Sinosauropteryx, the small terrestrial dinosaur found in China that first sparked that feather frenzy. In 2010, a team of researchers based in Bristol and Dublin managed to reconstruct the colors of its feathers.
They did this for Sinosauropteryx using traces of the pigment melanin. The same stuff that colours our hair and makes our freckles. So they've recovered evidence of this pigment in the feathers of Sinosauropteryx. And what they found was it had almost certainly colour banding along the tail. And when you compare with modern birds, and you look at things like a zebrafinch, they've got a fabulous striped tail and they use it for display, showing off fitness, advertising their quality to potential mates. So it's fairly likely that Sinosauropteryx was doing something similar.
Skin color in dinosaurs is, at least for now, almost impossible to discern. But using melanosomes, granules of melanin pigment, researchers can paint a remarkably accurate color picture of the feathers, at least.
We know that Microraptor, for instance, had a glossy iridescent sheen in its feathers. We know that Oinkiornis, a Jurassic dinosaur, it had feathers that were largely grey with some black and white stripes on the wings and a big red head crest.
But while melanin is a useful hint, it's only part of the color puzzle. Modern birds of every color have melanin in their feathers. It's other pigments that really flesh out the colors.
In the fossils, these other pigments decay away, and all we get left with is the melanin. So, it's like looking at a black and white, TV program. The colors you see, it's not like real life was all grey. You're missing that technicolor side of things.
I'd personally give Maria and her colleagues quite a bit more credit than to say they're still stuck in the black and white world. But even if the colors they're getting aren't perfect, our knowledge of dinosaurs has certainly changed. Not only do we know that they're feathered, we also know what they used them for, probably body temperature regulation and also for communication. So initially, most of the discoveries of feathers were found in the ancient ancestors of modern birds, and this is in a group of dinosaurs called theropods. Theropods are two-legged, hollow-boned predators, like velociraptors and T-Rex, a lot of the iconic dinosaurs. For a while, all finds of fossilized feathers came from theropods that existed late in the dinosaur era.
So it really seemed that feathers were an innovation that happened very late during dinosaur evolution. But then in 2014, myself and some colleagues, we reported complex feathers in a type of ornithischian dinosaur, let's say a distant relative of a triceratops. It's a dinosaur that has more ancestral features. It sits closer to the base of the dinosaur tree. It's called Calindrodromeus. It's from a site in Siberia. And it has 3 types of feathers. It has the simple filaments, which we've seen before in Sinosauropteryx. It has some weird ribbon-like filaments, which have been reported in theropods. And it has clusters of filaments. And these clusters of filaments really look like what we recognize as something like stage 2 in feather evolution.
What they'd found was that this dinosaur, with some really old characteristics of the dinosaur family tree, had the genetic ability to produce feathers. This means that the feather gene, so to speak, must have been old. So to see how old and where it fit into the whole feather dinosaur puzzle, Maria and her colleagues looked at another, much older branch of the dinosaur family tree, pterosaurs.
Many people think pterosaurs are dinosaurs because they were big reptiles that were around at the same time. But actually, they're a completely different family of reptiles and they share a common ancestor with dinosaurs. So they branched off during the early Triassic. They had wings of up to 15 to 20 meters, huge flying creatures. And I suppose just like with dinosaurs, we had thought that they were all just, dry and scaly. And we actually reported preservation of branched feathers in pterosaurs. And to be honest, that completely blew everyone's minds. It blew our minds.
If both pterosaurs and dinosaurs have evidence of feathers, that means the genetic ability to produce feathers started way, way back in a common ancestor. Feathers, says Maria,
they actually are a feature that evolved before birds, before dinosaurs. That they're a very ancient feature of this group of reptiles.
And because the feathers on these little baby pterosaurs were really tiny, Maria says that they couldn't have been used for flying. So the next best guess is that these reptiles used these little proto-feathers to regulate their temperature.
People think feathers are all about flight, but feather evolution is about your physiology, it's about your behavior, it's about where you can live. So you're looking at these different groups of organisms evolving feathers to keep warm. And that's telling us about reptiles transitioning in terms of their metabolisms. And once you change your metabolism and become warm-blooded, that opens up a lot of new habitats to you. It opens up a lot of much more active lifestyles.
I don't know about you, but the idea of even a few fuzzy, feathered, warm-blooded dinosaurs running or flying around the ancient world and using colors for communication, well, that's certainly not the land of dinosaurs that I used to imagine. At this point, I'm starting to question all of the dinosaur movies I've ever seen. In those movies, all the dinosaurs are huge, and all of the iconic ones, they all kind of lived at the same time. But both of those assumptions, it turns out, are wrong.
Most of those dinosaurs did not live together as one community. And so Stegosaurus and Tyrannosaurus rex never lived together. They're separated by, 100 million years of evolution.
This is Nicolas Campione.
I am a senior lecturer at the University of New England in Armidale, New South Wales, Australia.
Nick's done a lot of work on how big dinosaurs are and specifically how much they weigh.
The body size of an organism will dictate how it interacts with the world around it, its metabolism. And so we can use body size to explore the evolution of dinosaurs.
He told me that traditional understandings about the size of dinosaurs as these large, cold-blooded reptiles goes back to the 19th century, and it kind of has to do with human nature in a way. Who doesn't love to go find something cool, dramatic, and then show it off to the world?
The first discoveries of dinosaurs were very much focused on the sensational. They were focused on, let's find the biggest thing, let's find the big skulls, let's find things that, are museum pieces. And that very much framed our way of discovering fossils really early on.
The technique researchers used in the 19th centuries to estimate the size of these dinosaurs was pretty rudimentary.
So traditionally, the first methods for estimating size in dinosaurs focused on reconstructing the animal in some sort of live, I guess, a sculpture, effectively.
One famous 19th century paleontologist, and I should note controversial eugenicist, named Henry Fairfield Osborn, was a really big proponent of this method. He worked at the American Museum of Natural History with Charles Knight, a paleo artist. Together, they would make a little model of, say, a brontosaurus, and then use that to estimate weight and volume.
And once you have that reconstruction, you dunk it in water, find out how much volume is displaced, and that gives you the volume of the model. You scale that up to the size of the dinosaur, and voila, you have the volume of that dinosaur. And once you have the volume, you multiply it by some assumption for body density, and you have a body mass. It was crude for sure, but the funny thing is that I've gone on to make a lot of comparisons between the estimates and some of the bones of these animals. And actually, I find that some of these original estimates were not so far off. They're definitely within the plausible range of mass estimates.
This reconstruction technique has evolved quite a bit since then. Now, paleontologists use digital models rather than creating sculptures, but the principle is kind of the same. But in the last 150 years, a second approach has also been developed. This one estimates dinosaur size and weight by measuring their limbs.
It really just comes down to measuring bones and then testing to see how well they predict body mass in living things, and then making an argument about whether or not you think dinosaurs would have followed those same patterns. So in the mid-'80s, there was a paper written by Anderson, Dale Russell, and they were the first ones to propose, looking at living mammals, a relationship between the circumference of the humerus and the femur.
This approach was at first criticized. This was because the sample of living animals that they used to build the formula was originally pretty small.
So the work that I did, going back now to the early 2000s, was to try to test that. And so I compiled a giant data set of living animals, and each one of those skeletons was associated with a body mass.
Nick built a huge database of a ton of different animals. It included rhinos, giraffes, elephants, turtles, even an orangutan. He then calculated the ratio between the humerus, an arm bone, and the femur, a leg bone, for each of these different animals to see if it could be used to predict mass.
And I found that they were remarkably consistent. And I guess our assumption is that somewhere along the spectrum of living animals, dinosaurs are likely to fall within that.
Nick recently published a paper comparing these two methods, reconstruction and the limb measurement method.
Although the two methods for a long time were sort of pitted against each other, we've sort of come to find that for the most part, actually, they agree. Most mass estimates of the two approaches converge on very similar results.
The research that paleontologists like Maria and Nick are doing is certainly helping us get a better image of the ancient world. But a lot of their work also helps answer questions about deeper ecological processes. Nick's research, for instance, is helping to shed light on the evolutionary history of dinosaurs.
The first dinosaurs start off at one body size, kind of the size of a large dog, and then they radiate very quickly so that within, the first 10 or so million years, you've already reached most of the size range that dinosaurs would continue to have for the rest of their evolutionary history. It wasn't a gradual thing. It was very explosive.
This kind of quick change is called adaptive radiation. And uncovering more about how it happened to dinosaurs isn't just about the ancient world. It can also teach us things about animals today. For example, how they might adapt to changes or shocks to the environment. In a similar way, Maria McNamara's work on melanin, that type of pigment left behind in fossils, has also led to some surprising insights about the modern world. She found that melanin, it turns out, isn't just found in skin and feathers, it's also present inside the bodies of different animals, from birds to fish and even mammals.
In some species, we've up to 10 times more melanin inside our body than in the skin, in our skin and feathers. And we're coming to suspect that what it's doing internally is actually really vital in terms of metabolizing toxins, especially metals derived from the environment. Because we found that the melanin in different organs has a different metal signature. There's no clear reason for this, except that, the melanin in different organs is good at detoxifying different metals. It's mind-blowing, really. We're learning about aspects of how our bodies work that we never could have predicted 10 years ago. And it was stimulated by this work on fossil colour.
At least for me, I think it's super cool that studying animals that lived hundreds of millions of years ago can help answer some of today's questions. But fundamentally, I still kind of want to know what dinosaurs look like. So I asked Maria if she were to redo all those old dinosaur books that she found at her grandma's house, what would she change?
Number one, we would be incorporating dinosaurs of many different sizes. We would be including birds, because we now know that birds are just a type of dinosaur. They simply are the only group of dinosaurs that survived the end Cretaceous mass extinction. We would be showing dinosaurs flying, and we would certainly have dinosaurs with some evidence of what they looked like, and not just artists' flights of fancy. And we'd be talking about warm-blooded dinosaurs and also other things. We preserve dinosaur eggs now. We know that they took care of their young. I think it would really help bring them to life, actually, and make them much more tangible. Not these weird, unknown, ferocious beasts, but actually, in many ways, a lot more familiar to what we see today.
So Gemma, it turns out that in the 20 years since the first Jurassic Park film was made, and particularly in this latest installment of the franchise, the filmmakers have been incorporating a lot of new findings about dinosaurs and what they looked like into how they're portrayed on screen.
Don't give me any spoilers, Dan. I don't want to know what's in the film.
Of course, no spoilers, Gemma. I would never do that to you, but there are some fun things you could potentially watch out for in the film. First of all, feathers. They got that right finally, at least partially. There's a lot of feathered dinosaurs in this film. And according to a paleontologist who actually just wrote an article for The Conversation about the new Jurassic Park film, they got the colors much more accurate than they have in the past too. But of course, they did not get everything right. Not all the dinosaurs in the film that should have feathers do have them. According to the paleontologist who wrote for us, baby velociraptors should be kind of fluffy and look like baby chickens or something. And they didn't do that in the movie. That wouldn't be very scary after all. They also got the size of a lot of the dinosaurs kind of wrong, making them way bigger than they should be. Again, probably for the scare factor. So, pluses and minuses, maybe a B grade for the whole accuracy of the movie.
Okay, so we should give Hollywood some credit, but there's still a long way to go. And we should say that since we first ran this story back in April 2021, The Conversation has covered a bunch of other new research findings about dinosaurs. We'll put some links to those stories and some more dinosaur reading in the episode show notes.
Alrighty, friends, that is a wrap for this episode.
Thank you to Abby Beale, who used to work for The Conversation but has now moved on, to our friends at The New Scientist, and to Stephen Kahn for their help with this episode. And to Alice Mason for our social media.
You can find us on Twitter at TC_audio, on Instagram at theconversation.com, and of course, email us, podcast@theconversation.com. Don't forget to sign up for our free newsletter. It's actually really good, I will say. There's a link in the show notes. And of course, if you like what we do, please support the podcast and the conversation itself by going to donate.theconversation.com.
The Conversation Weekly is co-produced by Mariwany and me, Gemma Ware, with sound design by Eloise Stevens. And our theme music is by Neeta Sarl.
Thank you for listening.